Okay. So, welcome to the lecture 21 in this series in the course Classical Mechanics 1, and we will continue with the principle of mechanical symmetry, similarity, principle of mechanical similarity. So, in last lecture we were discussing the scaling scale invariance or scaling transformation and principle of mechanical similarity. So, let me remind you. So, in last lecture we have seen that if we scale the coordinates, all coordinates by alpha times Ri, and your time scale as alpha to the power 2 minus k by 2 times t, where k is the degree of homogeneity of the potential energy term. So, we have assumed the system T, the kinetic energy is quadratic, function of generalized coordinate, and U is a homogeneous function of Qi of degree k. And for that scaling, under this scaling we have seen that the Lagrangian will be just a constant times the old Lagrangian. So, once this properties happens, we know that L prime and L describe the same equation, motion dynamics will not change. So, we can scale our coordinates and time in this fashion to have the same dynamics. Okay. So, this we have seen in last class. Now, we will see what is the consequence of this. Okay. So, shifting all coordinates by equal time, we find that the path in the configuration space. So, let me draw the configuration space. So, this is configuration space, system was following this path. Now, if you scale all the coordinates, this will be replaced by a new path. So, what will happen that you have multiplying all the coordinates by equal amount. So, the path will have, so new path will have same geometry but different length scale. So, if it is our L prime is the new scale and L is the old scale, if we write like this, then this alpha is nothing but, so alpha is nothing but L prime by L, and I can say my r prime, the new coordinate will be L prime by L times r, and your t prime will be L prime by L times 2 minus k by 2 times t. Okay. And under this we will have the same dynamics. This we have understood from our previous analysis. Okay. So, basically we can write that t prime, from this last equation I can write t prime by t is basically L prime by L to the power 2 minus k by 2. So, this is the under scaling having two time length scale L prime and L. L prime is the new length scale and L is the old length scale. We can have t prime. Time t prime by t will be L prime L 2 minus k by 2 for a system where potential energy is a homogeneous function of generalized coordinate of degree 2. So, now how powerful this information that will check. So, for example, let us consider few examples. So, let us consider simple harmonic oscillator. The some system we will consider which you have studied and we know very well. So, the simple harmonic oscillator potential is half m omega square x square. So, it is kind of this. Potential is a quadratic function. So, k by our assumption k is 2, because we assume the potential energy is a homogeneous function of degree k. So, now it is half m omega x square. So, it will be 2. So, what will happen? T prime by t is L prime minus L 2 minus k by 2, k equal to 2. So, t prime by t will be 1. So, this implies that time period for a simple harmonic oscillator is independent of the amplitude. Okay. So, it is independent of the amplitude of oscillation, and this is something we know from our study of simple harmonic oscillator. We know that we will have more amplitude, particle will move more faster. When it is less amplitude, it will move slower, but the time period will be always same. So, this we know already, which we can extract from this principle of mechanical similarity by using this scaling consideration. Okay. Now, second example we consider that if we have a particle falling freely under gravity, so if I have a particle falling freely under gravity, then we know the potential energy is mgz. So, if it is mgz, that means k equal to 1, because it is linear in coordinate. So, k equal to 1, and then t prime by t will be L prime by L, and 2 minus k by 2 will be L prime by L to the power half square root of. So, this says the time of fall for a freely falling particle is proportional to the square root of initial altitude. Okay. So, this is also something some result which we already know, because these are very simple system and we know, but important point is that we extract these informations from the scaling by using the scaling of the system. So, we scale our coordinates and time in such a way that Lagrangian is multiplied by a overall constant, and from there that consequence we obtain this information. Now, let us consider the Kepler's problem. So, third example is very interesting. We will consider the Kepler's problem. Okay. For Kepler's problem, your potential is alpha by r. So, your k in this case will be minus 1. So, what happened? Let us go back to that formula which we obtain using mechanical similarity or the scaling behavior of the system is that L prime by L to the power 2 minus k by 2, but k is minus 1. So, it will be L prime by L to the power 3 by 2. So, this means your T square is proportional to a q, right. So, this gives the Kepler's third law. So, without proving the Kepler's law, we get a idea about the time period and its geometry of the orbit, how they will be related. T square equal proportional to a q, that Kepler's third law, using the principle of mechanical similarity. So, we will close this discussion of principle of mechanical similarity with this example, and now we will continue to another important topic of this course, which is called Virial theorem, and using this how we can get important consequences of a regarding the average kinetic energy and average potential energy of the system. Okay. So, if you we have finished the symmetries and conservation laws. If you have question queries, please raise in the discussion forum, we will try to answer. We will also have every month we will have a live session with the students. So, in that session also you can give your feedback, you can ask your questions, etc. Now, we will consider Virial theorem, and today we will start, and hopefully if you are able to finish it. If you cannot, then we will continue in next class. So, what is the Virial theorem? It is not directly related to the Lagrangian formulation, but it is very important, and a theorem which gives a lot of information about the classical system. So, we prefer to discuss it here. So, if you have a system finite system, then is finite number of particles and have motion in a finite region of space, then long average of kinetic energy is equal to minus half sum over Fi dot Ri, and long average of this quantity, sum over I for 1 to n all particles. So, summation is for particles, all particles, n is number of particles. So, this is the statement of Virial theorem. If you have a system, let me repeat, if you have system of n particles and moving in a finite region of space under the influence of a force Fi for the ith particle, then the long time average, if you allow this motion for long time and you consider the time average, long time average, mathematically it means for infinite time, then the long time average of the kinetic energy is minus half times sum over I equal to 1 to n number of particles, the force Fi dot with Ri. Okay. So, first we will prove this theorem, and then we will learn the consequence of the only thing important, that particle motion is having particle having motion in a finite region of space. Particle will never go to infinity. If you have n number of particles, they are moving in a finite region of space under the influence of force Fi on the ith particle, then the long time average of the kinetic energy will be equal to minus half times sum over I equal to 1 to n Fi dot Ri and long time average. So, this long time average of kinetic energy is given by this expression, is the statement of Virial theorem, where n is the particle number, F is the force acting on the ith particle, and Ri is the position vector of the particle, and the bar over it means the long time average. So, this is the statement of this. Now, we will prove this statement first, and then we will see the consequence of this. So, I can write this Fi, the force on ith particle, is the rate of change of momenta for the ith particle, and here we will assume that the kinetic energy T is quadratic function of the velocity. This is a very good approximation. We see most of the system, the kinetic energy is a quadratic function of velocity. Okay. So, if it is a quadratic function of velocity, the Euler theorem I mentioned about few lectures ago, the Euler theorem in mathematics says that sum over I Vi dot del t del Vi will be 2t. Okay. And also we have assumed that its potential energy does not depend on velocity. If you assume, then Vi will be del L del Vi. Okay. So, this will be further equal to sum over Vi, this will be dot Pi. Okay. And this will be equal to your 2t. So, let me write this sum over I Ri dot dotted with Pi, this is your 2t. Okay. So, this I can write is with simple arrangement that ddt of Ri dot R vector I dot vector Pi. So, first term I will get when I differentiate Ri minus the second term will be Ri dot Pi dot. Okay. So, let me write 2t equal to this. So, this we can write sum over I ddt of Ri dot Pi. So, I am forgetting I, should not forget on the vector, and minus sum over, let me write sum again, Ri dot Fi, because Pi dot is your Fi dot. Now, in this equation, so in this equation we will consider the time average. So, now we consider the time average of this equation. So, we consider time average of this equation. So, let me write left hand side 2t bar time average bar, and then I will take time average means if you have to this function you will integrate it over some interval of time 0 to tau, and you have to divide by the total time interval of this quantity ddt of Ri dot Pi minus, so I forgot summation. So, summation over I minus sum over I Ri dot Fi, and this integration over dt. So, I think you are familiar with the averaging for a continuous variable. So, it has to be integrated over a time, over a period, and that you have to divide by the period. Okay. This is the definition of time average. Now, we will calculate this integration. For the first part, we can explicitly calculate the integration because the total time derivative and that is integrated over. So, first part, so let me write 1 over tau, and the first part will have a sum over Ri dot Pi, and this is calculated over 0 to tau, okay, minus I will have 0 to tau integration sum over I Ri dot Fi dt, and 1 over tau is outside. Okay. Now, what I said is that okay, let me write long time average. What is the meaning of long time average? And please concentrate only on the first term. Long time average means tau going to infinity. So, let us consider limit tau going to infinity sum over I r I dot p I at tau minus sum over I r I dot p I. So, put a vector at 0. So, this quantity, and let us the other quantity I have that 1 over tau integration 0 to tau and sum over r I dot f I dt. So, I will not simplify the second term, and left hand side you recall that it is 2 t bar. Now, in the condition we mention in the statement of Virial theorem that particle number is finite, they moves in a finite region of space. So, if a finite region of space, the difference of this quantity 2 will be finite, and you recall that this it is divided by 1 over tau. So, we have a limit tau going to infinity, and we have a finite quantity by tau which will go to 0, because tau going to infinity, this limit will go to 0. So, this whole quantity the whole quantity will go to 0 in the long time average limit. So, when tau going to infinity, this quantity will be 0, and we will remain with 2 t bar equal to, and again we go back to the, okay, let me write first and then 0 to tau sum over I r I dot f I and dt, okay, and also limit tau going to infinity. So, we will not simplify this, and we can write, now we are almost in and a minus sign, there is a minus sign. Okay. So, you will get minus half times average r I dot f I dt. So, this is the statement of Virial theorem. So, the proved. Okay. So, let me recall that what was the statement of Virial theorem, that if you have a system of n particles, finite number of particles, and they are having a motion in a finite region of space under the influence of force Fi on the ith particle, then the long time average of the kinetic energy is given by minus half long time average of Fi dot r I sum over I equal to 1 to n, and this we have proved explicitly here. Now, we are going to see the consequence of this result. What is this result says? Okay. And for that we will consider that our U is a the potential energy is a homogeneous function of q I of degree k. So, this we are assuming. So, if we assume this, we can simplify, and f I is minus del u del sorry, not a homogeneous function of r I, we are using r I. So, r I. Okay. So, now t bar you can write with this assumption minus half sum over I r I dot del u del r I and the time average, long time average. But now we can apply the Euler's theorem again. Euler's theorem for homogeneous function. So, if we apply and it is degree k, then this quantity will be minus half k times u bar, because using Euler's theorem, Ri dot del u del Ri is Ku. K is the degree of homogeneity. So, this is the Euler's theorem. So, sum over I. Okay. Okay. So, what we obtain is that for this situation, when you have a conservative system, potential energy is a homogeneous function of degree k, then we obtain that T equal to minus this I am sorry, this is a mistake, this will be plus, it will be k by 2 times u bar. Also we know that total energy, average of total energy is the total energy, which will be T bar plus u bar. So, these two equations if we combine, then we get that if we substitute T bar here, then we will get u bar is equal to 2 by k plus 2 times total energy, and T bar will be k plus 2, k will be k by k plus 2 times u. This result will obtain from this Virial theorem. When this your system is a homogeneous function of degree k. So, now quickly we can see the consequence of this. For example, if you have a harmonic oscillator. So, example 1, if you have a simple harmonic oscillator, then your k equal to 2, because u equal to half m omega square x square. So, k equal to 2. So, in that case u bar equal to E by 2 equal to T bar. So, for simple harmonic oscillator, the potential energy average is equal to kinetic energy average, and that is a half of the total energy. Similarly, for a freely falling body, if you have a freely falling body, you have k equal to 1. So, you will have k equal to 1, u bar will be 1/3 of E, and T bar will be 2/3 of E. That this some result which is familiar to us. And third example, with this we will close this session. U bar for Kepler's problem. For Kepler's problem, k equal to -1, because potential is minus alpha by r. So, 1 over r means k equal to -1. So, if k equal to -1, then u bar is 2 E, and T bar will be minus E. The average kinetic energy is the minus of the total energy. This apparently looks some disappointing result, because kinetic energy is negative, but that is not true. This is a Kepler's problem is bound state problem, and we have E is always negative. So, kinetic energy is not negative, it is a positive, and this we obtain that average potential energy is the total 2 times total energy. And so, only last point that I will mention, and that close. If you have a potential alpha by r square, for that k equal to -2. Now, when k equal to -2, in the expression of the average kinetic energy and average potential energy, we have k plus 2. So, the denominator becomes 0, and this will create some problem to the system. So, but this is not inconsistent, because this system alpha by r square motion, the particle will move to infinity. So, motion is not finite. So, we will continue with this topic little bit more in lecture, but because we do not have time today, so we will conclude this lecture 21 here. So, we will continue, we will have a tutorial class in the lecture 22. Thank you.